There are a couple more things you need to learn about matrices. Um, so today is very simple, and first you have to know how to state the order of a matrix, which is basically its size. So if I had that matrix, what is its order? What is its size? It's always rows by columns. So we count the number of rows, and then we count the number of columns. So this, I'm not, really. 3 by 2. Yeah, okay, that kind of works. Of course, I would probably say that has 2, anyway. Yeah. So when we plugged them in for the matrices, this would have 3 equations, right? There'd be 3 x values, and then 2 columns. So however you want to remember it. Not a terribly big deal, but the only time you're really going to run into this is when you plug it into your calculator, and if you type them in backwards, it's going to be really obvious that it's backwards, unless it's huge, like 28 by 25. That might be hard to tell the difference of. Okay, well, what if I wanted to add another matrix to it? This is supposed to be a 4. Um, oh no. No, you wouldn't do this in your calculator. That'd take way too much time. It's way faster to just do it by hand. So in this case, can I add, let's call it matrix A plus matrix B? No. You can only add when they have the same order. They have to be exactly the same shape. Yes. So let's say we changed B, so it would be a little bit longer, like this. Now I can add, and it's very simple to add 2 matrices. You just add corresponding parts. So my result, if I take a 3 by 2 and I add it to a 3 by 2, my result is still a 3 by 2. And each one of these numbers has a position. So we would call this number here A11. So it's matrix A, and it's in the first row and the first column. So this number would be called A12. And then this number would be called A21, and this number would be called A22. And then similarly on the other side, this one would be called B21. Whoa, B21. Okay, so this one here, let's say that the answer matrix is C. That number there would be C11. And C11 is just the sum of A11 and B11. Does that make sense? So 1 plus 1 is 2. And then for C12, we would just do 0 plus 4 is 4, and 2 plus 0 is 2. 4 minus 3 is 1. Negative 3 plus 4 is 1, and negative 8 plus 8 is 0. Okay? Yes. So, what you might see today is a series of matrices and then a set of instructions. So you might have an A, a B, and a C, and you might get something like matrix B minus matrix C. Or not C, we don't have a C anymore. How about A? Matrix B minus matrix A. So that would be 1 minus 1 is 0. And then 4 minus 0 is 4. And then 0 minus 2 is negative 2. And negative 3 minus 4 is negative 7. 4 minus negative 3 would be 4 plus 3, which is 7. and then 8 minus negative 8 would be 16. Okay, does that make sense? There are two different versions of multiplication, and we're going to do the first one today, which is extremely easy, and then the second one is just really weird. It's not hard to do, but the reason that we do it that way is going to totally escape you, but we will work on that probably tomorrow. So today, you're going to be adding and subtracting and then do what we call scalar multiplication. So a matrix is just digital information. We take some situation and we convert the situation into numbers with nothing else, just numbers. So we have used the RREF button, and what you do is you take a system of equations and you distill it until you end up with just the coefficients and the answers, and then you ask the calculator to do this RREF, which is essentially elimination. That's basically what the calculator is doing, is elimination. It's a little more complicated than that, but the result is the same. And then we end up with a new matrix, and that matrix has been simplified to the point where it will tell us what the answers are. Okay? So when I teach matrices, I like to tell students that a matrix is sort of like a digital photograph, and each square is a pixel. Okay, now when you use your phone and you take a picture and it's like 16 megapixels, that's a huge number of pixels. But that matrix has so many pixels wide and so many pixels tall, right? And on your cell phone, it's a lot taller than it is wide, or you can turn it sideways. Okay, and every one of those pixels, so if this is your cell phone screen, wow, there are millions of pixels, and every pixel is a number. Actually, it's 4 numbers. Every pixel has a red number, a green number, red, yellow, blue, and black, or white, depending on how you look at it. Does that make sense? So pink, you would take a certain number of red, like the numbers are something like 0 to 250 or something like that. So there are 250 colors of red and 250 colors of yellow and 250 colors of black, and so every single pixel every single pixel has a red value and a yellow value and a blue value and a black value. And if the black value is 0, then that's pure white. No, it is a pink pixel, but that color of pink is a combination of 4 different colors. So if you think of it this way, if you were going to draw that picture, paint that picture, then every pixel would have a formula. How much red do I add to this pixel? How much blue do I add to it? No, yes. How much blue, how much yellow, and how much black? And yeah, it's like, so every pixel is a specific color, but that color is a formula that takes 4 parts into account. Does that make sense? It is. But every color is created using a formula that includes 4 parts. If all you do is add red, then you just get red. But how dark is that red? They're all the same red, but some of them are stronger than others. So if we had 100% red, 100% yellow, 100% blue, and 100% black, it would be really dark brown. Okay? If we had 100% red and 100% yellow and 0 on the other two, that color would be really dark orange. Does that make sense? So with a digital photograph, you can do things that you can't do with regular film. For instance, let's say we want to get rid of all of the red. All you have to do is go into every single pixel and change the red value to 0. Right? 255? So yeah, so there are 255 reds, 255 blues, 255 yellows, and 255 blacks. So if you want to know how many colors there are, oh, is it green? Oh, this is a subtractive wheel. Okay, that's fine. So if you want to know how many colors there are in a picture, just multiply 255 times itself 4 times. That's how many different colors a pixel could be. So when you, yeah, uh, it does, yes. Where is the color? All right, so look at this. So here is the color wheel. So let's say I want to make this color right here. Here's the formula. Don't worry about illumination. That's a computer thing. And saturation. So here are these 4 colors. 29 red, 232 green, 23 blue, and then the hue is probably black. Nope, the illumination is black. Okay, so saturation and hue we're not going to worry about those. But if I want to make that green color, I use 99 red, 238 green, 96 blue, and 157 black, or probably in this case white. Yeah. So see, it's adding white, not black. Okay, if I want this color, I have a different formula. So every one of those pixels has a value, right? Here is this value. Well, if you want to turn a picture black and white, it's really easy to do if it's digital, if it's a matrix. You just get rid of all of the red and blue and the green. And then all you're left with is black and white. Okay? If you want to rotate the picture, it's really easy. Turn your matrix that's vertical into a horizontal matrix and keep every number in the same place, and you will have changed it from portrait to landscape. Does that make sense? You can make all of the greens brighter. You can take out some of the red. You could make it more blue. And all you end up doing is altering these numbers. Every one of these numbers is linked to a pixel, and changing it is super easy digitally. Now, with the old film, there were all sorts of tricks to get rid of certain colors, but it was all chemical. It's what you had to do when you developed the film in order to make it like that. Or they would go in and they would paint on the actual negative. And so it's really quite confusing to do. So matrices are extremely valuable. Whenever your phone sends out information, it sends it out digitally in a matrix. And it sends it out in these packets. And then it comes in as a packet. And the old, I don't know if you guys remember this, but the old TV signals that just came through the air, you could just use a regular antenna. Those were analog signals. They were just frequency signals. Now they're digital. And if you have one of those old TVs, you have to get a digital converter, because your new TVs, they only read matrices. They don't read frequencies. So matrices are used all of the time. Well, one way to change matrices, let's say that I had a picture and I wanted to bring out the reds. So I'm going to take matrix A, and these are the red values inside a matrix. I want to make the matrix twice as red as it used to be. So 2 times A. What would that do to the matrix? It would double every value inside the matrix. So 2A would be 2, 0, 4, 8, -6, -16. Okay? Well, what if I wanted 2A minus 3B? I'm going to subtract the triple of B. So 3, 12, 0. And now I put them together. So 2 plus 2 minus 3 is -1. 0 minus 12 is -12. 4 minus 0 is 4. 8 minus negative 9 is 17. Negative 6 minus 12 is negative 18. And negative 16 minus 24 is negative 40. Okay. Now, that's very easy to do. But this type of multiplication is called scalar multiplication. Like you're changing its scale. So matrix A has been stretched, scaled, by a factor of 2. And if, for instance, it was a digital photograph and we were altering the reds became twice as red. So that's a really good question. So if I went here to find custom colors, let's say I picked this particular yellow. Nope, we need something that's less red. Okay. So I could make this green twice as red if I went in and changed that 64 and made it a 128. But this color system is set up to only make colors that you can actually see. And for some reason, women can see more colors than men. So if you look at two colors and you say, are these the same or different? Women can actually see more colors than men for some reason. Something to do with their eyes, or I don't know, some other reason. But if we started out with something like this, we obviously can't make it much redder because we run out of capacity. So that would be a limiting factor for sure. Well, you would end up creating a number that the computer wouldn't recognize, or the computer would be trained to turn it and just make it the maximum. I mean, if we started out with pure red, we can't make pure red any redder. So that would be a problem. Sure. So these are called scalars. They're called scalars because they scale the matrix. So you can multiply by a whole number or a natural number, and you can make the matrix larger. The values in the matrix just move out away from 0. So you can see everything that's in both of those is larger, or not, well, the absolute value of those numbers is larger than what we had before. Now you can scale by a fraction. You can multiply everything by 1/2 and it would shrink it. Okay, and that's one way to do multiplication inside a matrix. But it's not the one we use the most. We do use scalar multiplication, but there's another one called matrix multiplication, and it's really weird. It's not difficult, but it's really strange, and you'll look at it when we get there and you'll say, I don't know why we're doing this, and the answer really doesn't come out in this class. I'll do my best to explain it. But if all you want to do is change individual colors, then you can just use scalar multiplication. But if you want to rotate a matrix or reflect it, if you don't like how your picture looks, you can flip it this way, or you can flip it upside down, or you can rotate it, or you can do all sorts of other crazy transformations, like put a doggy nose on somebody, or give them a double chin. All of those are done using a matrix, through using matrix multiplication. Oh yeah, definitely, totally. They they um, so it's actually really easy to do. If you understand how matrices work, it turns out that every filter is just one set of, it's either one matrix or one set of matrices, and all it does is multiply. It takes what you have and multiplies by this particular matrix, and that will alter the picture in the way that they want it to be altered. And once you figure it out once, it's really easy to just change it and figure it out in a different way. So everything digital is manipulated through matrices. And again, there is an entire class that deals with matrices called linear algebra, and it will teach you how to do all of this stuff. It's really quite amazing. Okay, so our assignment is 8 840, I think 842 was right. 842, 1 through 24. Yep. Oh, so I didn't show you part of this. Sorry. I got sidetracked. Look at number 10. Number 10 has two matrices. So we have one matrix is equal to another. Can you tell me what X and Y are? Well, this has to be equal to that, and this has to be equal to that. Yeah, all. And then look at, do 14. So 9, 2b plus 1, negative 5, and 16. And that matrix is equal to a squared, 9, 2a plus 1, and b squared. This one's a little bit trickier. So what do we know about this? So a squared equals 9. So a is equal to plus or minus 3. Okay. And b is equal to plus or minus 4. But good. We have another thing we need to look at right here. Does 4 and negative 4, do 4 and negative 4 both work? No, just the positive 4. So B is just 4. And then if we look at this connection, does the positive 3 work? No, but the negative 3 does. So A is negative 3. We get rid of this one, and we get rid of this one, because they have to work everywhere. Let me look at 11. Okay, so 11, x plus y equals negative 5, x minus y equals negative 1, and z is 3. So you just have a linear system, right? You have x plus y equals negative 5 and x minus y equals negative 1. You can use substitution, elimination, or RREF. And we don't need to include z because z is 3. Did you do that in your head? I'm impressed. So x plus y, oh, I killed it. Well, just set it up as a matrix and stick it into your RREF. It is set up for elimination, so that might be a faster way. So you have x plus y equals 5, negative 5, and then x minus y equals negative 1. So you can do substitution, elimination, or matrix. So 842, 1 through 24, all. On the first set, all you're doing is stating the order. 3 by 4, 2 by 8. And then in the next set, you're solving. And then in the next set, you're doing the addition with the scalar multiplication or subtraction with scalar multiplication.